Hi everybody, welcome back. Last time we introduced the concept of thermodynamics, which literally means the motion of heat. And one particular example we had this block of steel that was hot. We put it into some cooler water, and the heat transferred from the hotter block into the cooler water until they finally reached equilibrium. So how much temperature change we got for a certain amount of heat depended upon a quantity called the specific heat. And the specific heat was a property of the material itself. It wasn't a variable that we could change really. And most of the time it was measured by a material scientist who figured out what it was, put it in a book. You put that book on your shelf and then you pull it out whenever you need to work on your design. But there are other thermodynamic properties that we need to deal with. You've probably experienced it yourself. At night when the air starts to cool down, you may have heard your house creaking. And that's because the wood beams are contracting just a little bit. And you've probably experienced this a lot as well. If something heats up, then it's going to expand. If something cools down, it's going to compress. Well, the amount at which that occurs then is another property of the material itself. And so we measure the strain on the object being its change in length relative to its total length. So you can kind of think of it as a percent change from that. And then how much of a strain you get depends upon that characteristic coefficient of that material. And again, material scientists find this for you. You pull your book off your shelf, you look it up, and then you go on with your design. But what material you choose has a lot to do with how your object, how your structure is going to respond thermally. And you might choose a different material for a hot, dry desert climate than you would for a cooler, wetter, swampy climate or something like that. So we're going to look at the idea of expansion of materials, and of course that could be contraction as well, so that you can get an idea of how this process works. Let's get started. Okay, so if you've ever been to our in-person lab and worked with our robots, you probably noticed that the structure of those robots is made out of this kind of bluish colored aluminum. Now, aluminum itself, of course, is just kind of silver, it's reflective. These particular beams have been anodized, which is a chemical process that gives it kind of a decorative color, blue in this case, and also helps it resist corrosion, wear and tear, things like that. But essentially, it's still just an aluminum beam. It responds like an aluminum beam. So aluminum, it turns out, is an excellent choice for designing a structure for these robots. It's reasonably light. Remember that our motors on our robots aren't very strong, so we want to keep the mass down. It resists bending. It resists wear and tear, but it also resists being able to expand due to heat. It's not going to expand very much at all. So all of those things together mean I can take my robot, I can put it out in the sun, and I can still run whatever obstacle course I want to run, and I don't have to worry about the structure of the robot not maintaining its cohesion with there. However, even though the expansion isn't much, it is there. And we as engineers always need to check how much that expansion is to make sure it's not going to cause us problems. So we're going to have to figure out how to determine how much that beam is going to expand depending upon how much heat we put into that beam from there. Now, probably the most common thing you're going to do is take it out in the sun. Now, we know that the structure heats up just from friction as it slows down, because friction is effectively thermal energy. Now, as we saw last time, it's not much, but certainly I could put it in the sun. Maybe it's going to get exposed to an open flame. These are BattleBots, who knows? So we want to know what's going to happen with that. So we need to come up with some sort of mathematical expression that'll let us calculate that. So take a look at Microtask 1. Suppose we've got a beam here, and we'll just idealize it as a rectangular beam here. And suppose it's got length L, and then we heat it up. Well, it's going to expand. And the amount that it expands by, we're going to call delta L. That's the change in the length. All right. Now, you may say, well, Dr. K, isn't it going to also expand in width this way? And yes, actually, it will. However, if this is the width, delta W is going to be much, much smaller than delta L. And so for a beam like this, you're not going to be able to see it. You're not going to be able to measure it. So we're okay neglecting that for now and just treating this as a one-dimensional object in that case. So what I want you to do is pause the video, kind of brainstorm what you think might be going into causing this expansion? What kind of physical properties or processes would be causing this beam to expand? Because we need to identify all of those so that we can come up with a mathematical expression. Pause the video, do that now. Come up with some ideas? Well, one thing you might have thought of, certainly, is thermal energy, right? Heat. Heat is thermal energy. Thermal energy is heat. There's no difference between them. So the thermal energy is what's going to make it expand in the first place, right? So thermal energy certainly has to be one part of our equation. The second thing, though, do all materials expand by the same amount, by the same percentage? Actually, they don't, and so it depends a lot on what that structure, what that material is made out of. So we're looking at the molecular structure. Now, notice that we're talking about this kind of percentage change. That way I don't really have to worry about how much mass I have and things like that. So these are going to be the two main things that I need to have. So I can, a lot of things in engineering are not under my control, but the type of material that I choose for a particular project is under my control. And for example, if you're building a bridge, aluminum is a terrible idea for that. It's not going to make a good bridge at all. You're going to want to use steel or concrete, something like that. All right, flip over to the next page and let's see if we can figure out how to get this equation. All right, so we've identified two things that are going to make that beam expand. And one was thermal energy and the other was some sort of property of its molecular structure that we won't get into the details of unless you become material scientists. So, however, we do know that as I add thermal energy, I also increase the temperature. There's a direct relationship between these two. We studied that last time. So, but which is easier to measure? Is it easier to measure the thermal energy or is it easier to measure the temperature? It's a lot easier to measure the temperature, right? No matter what kind of material it is, I can always measure that temperature a lot easier. So we're going to define our equation in terms of the temperature, but understand that that is just the thermal energy with some constants in there, all right? So we're going to define what we have in terms of the temperature. So we know then that our percent change that we were looking for is delta L over L must be some constant times our temperature change. Now this delta L over L is a bit tedious to write. Any length change over a length is called the strain. And so one that's caused by heat, by thermal energy, is simply called a thermal strain. So this symbol right here means strain. It literally means change in L over L. However, if I put a little t next to it, that means this is the change in L over L caused by thermal energy. And there are a lot of things that I could do to change this, but we're only going to deal with the thermal energy. So big thing that I want you to remember here, though, is this right here. This is not the coefficient that depends upon the molecular structure. This is just a shorthand for writing this fraction right here. Right? So rather than having to write this fraction, it's equal to this. But you do need to remember that delta L over L is equal to that. It's just another symbol as a shortcut. All right. Now, looking at the way we've written it here, is the percent change in length, this thermal strain, how does it vary with the change in temperature? As the change in temperature goes up, does this percent expansion that you want to think about, does it increase or does it decrease? Well, they're both going to go up, right? As I heat up, it's going to expand. So we know that they must be directly proportional. All right, so we know that there has to be some sort of a constant of proportionality here. And so that constant of proportionality, in this case, we use the symbol alpha. And this then is our equation for determining our thermal strain. Don't forget, though, this is just shorthand for writing this. They mean exactly the same thing. So both of these equations are saying exactly the same thing, but you need to learn to recognize that symbol right there. All right, so I would look this up in a book. Unless you're a material scientist, you're never going to worry about calculating that. It's already been determined for you for practically any material that you could ever want to use. You just pull that book off your shelf, you open it up, you find that material, and there's your thermal strain coefficient. Okay? So we need to have some units for this, as always. First of all, what are the units of the thermal strain? Well, look at its definition here. You can see it right there. So delta L has units of meters, and L has units of meters. So the thermal strain must have units of nothing. It's dimensionless. So it is a dimensionless constant, or a dimensionless term, which makes sense, right? Because it's really just a percentage when it comes down to it. So L over L, or this epsilon t, have no units. Delta t has what units? Well, it depends on what particular unit system we're using, but we need to use Kelvin because our alpha will be expressed in Kelvin. So just like we talked about last time, we really need to make sure that we're doing all of this in degrees Kelvin from them. You do remember, though, of course, that my change in Kelvin must equal my change in centigrade in this case. Do it all in Kelvin, then you won't have to worry about it. All right, so here I need to get something that has no dimensions, and I have something with unknown units times Kelvin. Well, then its units just simply must be 1 over Kelvin. So the units of the thermal expansion coefficient is 1 over Kelvin, which we will often write as Kelvin to the -1. Those mean the same thing. So just get used to seeing both of those. So when you look this up, you're going to get some number with units Kelvin to the -1. All right, let's look on the next page. All right, so now let's see if we can do an actual problem with this. So here I've got a beam, and this beam is made out of our anodized aluminum, and it's got some length L, and we're told that L is equal to 20 centimeters. So this is 20 centimeters. Okay, and we're going to increase the heat, we're going to add heat so that the temperature change is 40 degrees centigrade, 40 degrees Celsius. So we want to find what is the thermal strain, and we want to know what is the length after it's heating. Okay, so remember our thermal strain is delta L over L, but then I want to know what is going to be the final length. This L is always going to be my initial length to start off with. All right, so our scenario is going to be find the thermal strain and the final length of a beam. And this could be one of the beams that you're using to build your robot with. All right, so our diagram is going to look something very similar to what we have here. We're going to have our beam that has a length of L, which is 20 centimeters. And then it's going to expand to something that looks like this. And so it's going to expand by delta L. Okay. We want to know what is going to be the total length. Well, the total length, L total, is simply going to be its original length. Let's go ahead and put a 0 by that so we know, plus how much it changed by. Makes sense? Just look at your picture and you can see that, right? So this length here must be my original L0 plus however much it changed. So once I find that thermal strain, finding the delta L is going to be very easy, and then I just add it to my original length. All right. So let's lay that out explicitly. So we're going to find the thermal strain for the delta T that's given, and then we're going to use the definition of the thermal strain to find delta L, and then finally we will add delta L to our original length to get the final length. All right, so let's write down our equations. Well, first we'll do our symbols. Sorry, we'll do our symbols first. So we know that delta T then is equal to 40 degrees centigrade. We know that our original length is going to be 20 centimeters. We know that our coefficient of thermal strain is going to be 2.30 times 10 to the -5 Kelvin to the -1. And what I want to know is what is my total length. Now, it's a good idea to go ahead and convert everything to meters, but you don't necessarily have to in this case. Notice that because my units cancel out here, whatever units I have for L's, for my original L, are also going to be the units for my change. If it makes you uncomfortable to work in something other than meters, kilograms, and seconds, it's perfectly fine. Just go ahead and change it. Because remember, 20 centimeters is nothing more than 20 times 10 to the minus 2 meters, right? That centa tells us is 10 to the minus 2. So the conversions are not difficult. But to get some practice, let's go ahead and leave it in centimeters. And that's one of the advantages of writing our system this way. That's why I want to do it this way, is because this term is dimensionless, then whatever units I have for my original length are also going to be the units of my amount of expansion. So it's really convenient. All right, so we're going to leave our L total in centimeters. Now we do know that we're going to need to find delta L, and we don't know what that is, but we know that it's in centimeters as well. Okay, all right, so let's go to the next page and let's look at our equations. All right, so our first equation then is just going to be our thermal strain, and we know that that's going to equal this times delta T, right? So this number right here is a property of the material, and then this is the amount of temperature change, and then this is my thermal strain. I can define this as this, delta L over L, but it's also okay to go ahead and put it directly in this way, as long as you recognize that that's what this means. That's the important thing. But you're going to just end up substituting this in for this anyway. So if you want to start with this, that's perfectly fine. Then finally, for our step 3, we said we were going to get our total length was going to equal our original length. This, by the way, is also our original length, plus our delta L. Okay, so now we're ready to go. So first thing is we need to find that thermal strain. That's this, and we know that that's equal to alpha times delta T. Well, alpha, looking at our notes here, was given to us to be 2.30. So 2.30 times 10 to the minus 5 kelvins to the minus 1, and our temperature change. Now our temperature change is 40 degrees C, but I need it in Kelvin. But remember what we said, our temperature change, delta K, is equal to delta C. So this delta T was my change in temperature. So that's also 40 degrees Kelvin. Now if you don't like that, it's perfectly okay to convert your starting and initial temperatures. But in this case, we're not given a starting initial temperatures, are we? But let's say you made up a starting temperature, converted to Kelvin, added 40 degrees Kelvin to that, you're still going to get 40 degrees. So keep this in mind, that my degrees Celsius and my degrees Kelvin are always going to be the same. Okay. All right. They're going to be the same if we're doing our change, because 1 degree Kelvin is equal to 1 degree centigrade. So 2.3 times 10 to the minus 5 times 40 degrees, and that gives us 0.00092. And there are no units for that. There are no units at all for that. So this is the answer to my first part. And if you're thinking of it in terms of a percentage, it's very close to 0.1%. So it's going to expand by less than 1%, about 1/10 of a percent. So that's not a lot. That's probably going to be a pretty good design for us. All right, so that answers the first part. The second part, then we want to find our total length. So our total length then is going to be L0 plus delta L. So that means I need to find delta L. Well, we know that this is equal to delta L over L. And so delta L, this is L0, is equal to our thermal strength times L0, which is going to be 0.00092, no units, times my initial length, which is 20 centimeters. And so if I multiply that number by 20, then we get that delta L is equal to 0.0184 centimeters. So it's only going to expand by about 2/100ths of a centimeter. That's not much. No, that's less than a millimeter. So that's going to give us a nice stable material for making our robots out of. But now we've actually been able to prove how much it is. My total length then is going to be 20 centimeters plus 0.0184 centimeters, or about 20.02 centimeters. That's going to be our final length. And we predicted it would be about 0.1%, and sure enough it is. Okay, so that is an example of how we would calculate how much our materials are going to expand as a result of the thermal energy that's put into it. And you can see it's not terribly difficult. Now, Aluminum is an excellent choice for making robots. You may have seen Lego Mindstorms. That's another robotic system that's commercial, but it's fairly popular. Now, Legos are made out of ABS plastic. So the the coefficient here is quite a bit different. It's 1.5 times 10 to the minus 4 Kelvin to the minus 1. So let's suppose that we have that same beam that's 20 centimeters long. So L0 equals 20 centimeters. But now it's made out of ABS plastic. So it's expanding, and it's going to expand by a different amount for the same amount of temperature. Okay. What I want you to do is now stop the video. You've got all your equations laid out. Go ahead and figure out what is going to be the final length, the total length, after we add this 40 degrees of temperature. Pause the video, do that now. Have you got it? All right, well, the steps are already laid out for us. We know that this is going to equal alpha delta T. And so alpha in this case, though, is 1.5 times 10 to the minus 4 Kelvin to the minus 1. And we still have that 40 degree Kelvin temperature difference. So let's multiply that out right quick. So we get 1.5 times 10 to the minus 4 times 40. And now we're getting that our thermal strain is 0.006. So instead of 0.1%, we've got about 0.6%. So it's going to be about 6 times as much from that. Well, let's work out what our total is. We know that this is equal to delta L over L. And so delta L is just going to be this. Right, and so that's going to give me 0.006, no units, times 20 centimeters. Put that in your calculator, times 20. And we get 0.12 centimeters. And so my final total length then, after the expansion, is going to be 20 centimeters plus 0.12 centimeters, which says that L total is now going to be 20.12 centimeters. Now that may not seem like a lot. However, remember the way Legos work. The holes on the bottom have to exactly line up with those pegs that are on the top. Otherwise the Legos won't snap together. So changing it by a millimeter or so is enough to make it so that now for this big long plank, now the pieces on the end are not going to line up, and you're not going to be able to plug your pieces back into it. So Legos actually are not as good a material as aluminum. Now, as long as you're doing your project indoors, the chances of you heating it up on a hot summer day are pretty small, and you're probably not going to notice things. But if you're trying to take your robot outside, there's actually a really good chance that you're going to mess up the structure of your robot. The aluminum is going to be a better choice for that. All right, look on the last page here, and just a couple of other things that we want to sum up. Now, remember that we said that our beam had some delta L that it was expanding. Maybe it went from here to here, and so that was delta L. And we said that that was going to be much smaller than this delta W here, and so we were neglecting it. But what if I have something like this? Well, now the change in W, the change in my width here, is certainly not going to be negligible compared to my change in length, because they're basically the same size. That's not a problem. Now instead we just talk about the area instead of the length. And so we will define our superficial expansion, so our superficial thermal expansion, is the change in the area, over the original area. And for that we use a symbol called beta. So that's the coefficient, I'm sorry, beta times delta T, whoops. So that's our coefficient that we use for measuring this change in area. This is going to be also determined by the properties of the material. However, if you look at the material, you're going to find that this number is always twice my alpha. And if you think about it, it makes sense because we're expanding in 2 dimensions. So the area change is what I would be interested in looking at this, because I'm expanding in 2 dimensions. But getting beta is no more difficult. I just do 2 times my alpha with that, and that'll tell me what percentage that my change will be. So you think about it, for the same temperature change, my area is going to grow twice as much as my length would, simply because I'm expanding in 2 dimensions. So similarly, if we are changing in 3 dimensions, that's called a volumetric expansion. So here I'm going to have a cube that looks like this. And we use this symbol gamma for its property. Now here we want to talk about the change in volume. And so this volumetric strain, thermal strain, is then going to equal gamma times delta T. Because now I'm expanding, and of course I'm not going to be able to draw this, but I'm expanding into a larger cube. So the whole volume is changing here in this case. Hopefully that gives you an impression of what's happening. The whole thing is expanding. Well, you can probably guess how gamma relates to alpha, right? We're expanding in three directions instead of just one, so it's going to turn out that gamma is just equal to 3 times alpha. So none of this idea of expanding in multiple dimensions is actually any harder. You just have to remember, oh, I am expanding multiple dimensions, and I just multiply by the number of dimensions I'm working in. And then remember that I'm not changing in length. For example, here I'm changing in area, and here I'm changing in volume. Other than that, there's no difference. So there's always trade-offs in choosing a material. Legos are extremely light. And so therefore you can get more power, more velocity, for example, out of the same motor than you could with a heavier aluminum. However, as we've seen, they're not as strong. So the adage is in engineering basically is a material can be cheap, light, or strong, but you only get to pick 2 of them. So you could create a material that is both light and strong, like a nanocomposite or something like that, but it's going to be extremely expensive. Other than that, you can make it cheap and light, or you can make it cheap and strong, but that's pretty much going to be your only choices with that. So part of the art of engineering is not just developing the design of the structure, it's deciding what you're going to make that structure out of. And it's a consideration you have to keep in mind. Now, the study of thermodynamics has a lot more involved in it than our just basic introduction that we've done here. We can exchange heat. We can use that to create power. That's going to be a heat engine. We can have it do work. There's all kinds of things that we can do with this. And the different properties of it, the pressure, the volume, the temperature, something called the entropy, the enthalpy, and a number of other physical properties end up changing. And by tracking those changes with the exchange of thermal energy, we can figure out how these different types of devices will actually work. And so that's going to be one of the main thrusts of your thermodynamics class after this one. But it's important that you keep in mind the concepts that we're dealing with here. That'll serve as the base that you'll need for some of your later classes. We'll see you next time.